Okay. So any questions regarding the project assignment, homework? You don't have the second homework yet. I'll update the second homework.
Can we have more test cases? The previous project like has 30 test cases. This one like has 10.
This one has 10 test cases.
Yes.
Well, those are the test cases that you need to pass in order
So if you are passing all them, it's
should be, and the grading test cases will be bigger, longer, but it should not have any surprises. You're grading the project, right? So you should receive grades by today, the first project, and then you see where you went wrong. So come to during the office hours. Come, the graders will post their office hours, so you can come there and check what happened to your code and what happened to your solution and so on. So if you do not get full points, please do come and check what went wrong. Yes.
When should we be getting the grades back for the midterm and the homework?
By this week.
By this week? Okay.
Any other questions? Okay. So let's go and we'll start a new topic. We'll talk about the runtime environment. So when we are dealing with semantics as well as types, what we saw, especially with respect to semantics, we were drawing those box and circle diagrams, right? And we saw that by using certain different types of scoping, we get different results for different programs. And what we discussed was, if we have some code that is not correct with respect to scoping, or which is ambiguous with respect to scoping. Also, if we have dangling references or garbage, different runtime environments handle it differently. That's what we discussed last time. So if you have a garbage location and you try to access it again, some runtime environment might give you 0, some other runtime environment might give you some random value. Again, if we take a variable and free that variable or deallocate it, and we then try to access a deallocated location, so a dangling pointer. So if you want to try to access that dangling pointer, then depending upon the runtime environment, you get different results. So we now will discuss the runtime environment, how different runtime environments work, what do they do, and we'll talk about specifically the location and name. So we'll talk about those box and circle diagrams. So whenever you have a name, how the location is resolved for that particular name, and when you do deallocations, when you do garbage values, what happens to that location. We will also discuss how do you resolve a name to a particular location. How do you resolve that? What is the exact mechanism followed by a runtime environment? So we'll talk about that. So we'll talk about locations and names. What is the semantic distinction between location and names? How do we distinguish between these two? Then how does the compiler actually implement locations and names? How does the compiler map names to memory locations? We will talk about all these things. Right? All these questions we'll answer. And we'll answer these questions by assuming the C scoping, which is the static scoping. We'll assume the static scoping and answer those questions. So now let's go step by step. So the first thing that we know is global variables. That we know that there are global variables. So where can the compilers put global variables? We know the answer to this. Where do they put them? In some memory, right? RAM. So you can put them in RAM memory. You can put them in registers. You can put them in disk, cloud. Many different options are there. What are the constraints on those variables? We have access constraints, who can access them, who can't access them. We specifically mention all those things, right? So let's take an example. Let's say we have these. All these are global variables. A, B, C are global variables. So who can access them? Any program inside that file can access them. Even if that file, if a particular code is not a part of this file, so you can still access those variables. If you had declared them static, you won't be able to access. But since we haven't declared them static, we can access those. So now let's say we do this. A equals 10, B equals 100, C equals 10.45, and then we do A equals A plus B and return 0. Where do we keep all these variables? That is the question we want to answer. So as he said, we keep these variables in memory. So whenever we declare ABC, we know that we have to draw the box and circle diagram, right? So which means that associated with each A, B, and C, there should be a memory. There should be a memory address. So let's say the address of A is capital A, that of B is capital B, and that of C is capital C. So what do you do for the first line, A equals 10? What do you do? This we have learned talked about maybe 3-4 classes back, right? If we imagine box and circle diagram, what do you do if you do A equals 10?
Value address A.
So the value 10 goes into the address A. So memory address A has the value 10. Right? Similarly, if you do B equals 100, memory address B has the value 100. Right? And similar for C, memory address C has the value 10.45. Now what happens when you do A equals A plus B? The result should be memory at A, or value at memory address of A should be memory address of A plus memory address of B, or not memory address. So value at memory address of A should be equal to value at memory address of A plus value at memory address of B. Right? That's what we want. Now let's see what happens in really in practice. So what happens is that whenever we write this code, we compiled it in one of our machines in the Intel lab, and I could extract the memory addresses. So whenever you have int A, you go to that memory address. Now that is a memory address in the RAM. Is that stack? Is that memory for the program? We don't know. We don't know it yet. Okay. Turns out that it is not the stack. Stack has a different start address. So this memory address is not the stack. It is in the RAM. It is the program memory. So A goes to that particular memory address. Now why it is that particular memory address, we don't know. It's just the memory management unit of the operating system gave us that address. Right? So there is no specific reason why A is at that address. But once A is at that address, then where will B be? Turns out that B is in this address. And notice the difference is 4. The difference between address of A and address of B is 4. Why? Huh?
That's the size of int.
That's the size of int, 4 bytes, 32 bits. Right? That's the size of int. So it is a 32-bit system. From this you can understand that this is a 32-bit system. It's not a 64-bit system. Because for int it keeps 32 bits or 4 bytes. Now where will C go? Which is this hex. So you have 3, 9, 3A, 3B, and then you get C. So you get C at 3C, right? Now what is the first line of code? A equals 10. we will have to look into the assembly. So what happens in the assembly code is a equals 10 gets represented as move L. So this is a different instruction than just move. So move L means it operates with L value or location. It operates with location, which means it takes the value A, puts it into that location. Right? So equals 10 means A. What does A mean in hexadecimal? A means the value 10. Right? If you convert from hexadecimal to decimal, A becomes 10. So you move A to the location 8049634, which means this was the location of A, the variable A. Right? Then you move the value 100 to the location of B. So 64 in hexadecimal, if you convert to decimal, it becomes 100. So move the value 100 into the location of B. So exactly what we thought, that's what happened. Right? You take the value 100, put it into the location of B. Now what happens with C? Now C is a little bit different because C is float. So float is handled much in a different way than integers. So how do you handle float? You first do this. What is this? What is EAX? What is move? Move is different from move L. Move L means it is associated with the location. Move is not associated with the location. Move is associated with the register. That register does not have any location, does not have any address. Right? That value 0x41273333. What is that?
Register.
What?
That's the register.
No. Yes.
IEEE representation.
It is IEEE 754 representation of the value 10.45. It's the representation of float numbers. Right? So that is the representation of 10.45. So what you are doing is you are taking that float value, putting into the EAX register. So that percentile EAX, that is the register. It's the CPU register. It's not a memory location. That is not a memory location. It is a register inside the processor, inside the CPU. So you first put that weird number, IEEE representation of 10.45, put it into the EAX CPU register. Then what you do is to take whatever is the content of EAX CPU register, put it into the address of C. So whenever you have float, C is equal to 10.45, it's actually two steps. It's not just one step. What you do, first convert the float value into IEEE representation, put it into the EAX register, whatever is inside EAX register, then put it into the location of C. Right? And remember, this is move, not move L. Whenever you have a register, you use move. You don't use move L. That's the assembly instruction. Then you have A equals B. Now, what did we say before? We said that this A equals A plus B is 3 steps. We said we talked about register R1 and R2. Right? We said that we put the arguments in R1 and R2, add them up, send it to another register. Right? So, what happens? You first move whatever is in A, move it in the register EDX. So that is R1. R1 is EDX. Okay. Then what you do is you put B into the register EAX. So EAX becomes R2. Right? Then you do something very different. We haven't talked about this. Then you use this instruction EAX. You pass 3 arguments to it: EDX, the register EDX, the register EAX, and 1. And whatever is the value, you store it back in EAX. So what is happening here? What is the deal? LEA is a special register or it's not a special register. It's a special operator which does the following. I cannot zoom out because this is broken. I will tell I already told the IT people to fix this, but for now we will work with this broken thing. Okay, so LEA. So we have LEA. We have this instruction, right? So this instruction does the following. It basically calculates A, B plus C. This instruction is one instruction to calculate this, A, B plus C. Right? So what is A? This is A. What is B? This is B. And this is C. So that is what this instruction computes. So AB plus C means it multiplied percentile EDX, multiply it with 1, right, and add whatever is in EAX, and it puts it into the register EAX. That is the function of LEA. Now using this LEA, you can do addition, you can do subtraction, you can do multiplication, whatever you want. Right? How will you do subtraction?
-1.
Yes, just instead of 1, have -1. You can do subtraction. Right? So that is what it does. So this is 3 steps as we discussed. No, we discussed 2 steps only. So first you move the value of A. No, value of B. Where did we start? Oh, here. Okay. So this is 3 steps. So we first move the value of A into EDX, then the value of B into EAX, then do this EDX, EAX, 1, and store it into EAX register. Now once we store it into EAX register, we need to take that EAX register and put it back into A. That's what we did. A equals A plus B. Okay. So this A equals A plus B is actually 4 instructions. A equals A plus plus, or A plus plus is 3 instructions. But A equals A plus B is 4 instructions. Why is A plus plus 3 instructions? Because you don't need to do this. You don't need to move the value. Instead, what you do is LEA percentile EDX. So this register, 1, 1. That will give you A plus plus. Right. So that's why it's 3 instructions. But A equals A plus B is 4 instructions. So you do all this, and then you are basically done. Right. So when we have global variables, then all the variables are in some memory location. That's not the stack. It is the program memory location. And that's how you operate. You take the memory location, put it into, or whatever value you have in the memory location, put it into registers. Then you use the registers to operate this LEA instruction or whatever. This can only take registers. This cannot take memory locations. LEA instruction can only take registers or constants as input. It cannot take memory locations. So you do LEA and then you move the result into the appropriate location. So that is what you do with respect to global variables. Now what do you do for local variables? What are the constraints? Where can compiler place the local variables? Where do they place the local variables? Stack. Why do they place them in the stack? Why not place them in the global area? What is the problem? If we have global memory and we just keep one chunk of global memory for each function, what will be the problem?
Once we exist the function, we don't need them.
Yes, we don't need them, but we will override them.
Access, like, you want to have access to that memory, right? Override it.
No, you cannot override because our operating system will stop you from overriding.
The stacks are dynamic.
Close stacks can change size. You can limit stack size. Right? You can put some variables from the stacks and throw them away. Put other variables in. So stacks are dynamic. Global memory is not dynamic. It's fixed for a given program. But stack size can change, can increase and decrease. So what is the advantage? So if you have this type of a program, what will happen? If you have this type of a program, so this is your computing factorial, right? And you keep on incrementing n, and you say that these local variables, right? These local variables are stored in the global memory. There is no stack, right? What if you have factorial 2? How much memory will you need? If you have factorial 2. How many function calls will you do if you have factorial 2? There are 2 function calls. Right? Factorial 2 and then again factorial 1. So you need just 2 memory frames for each function. Now if you have factorial 100, how many calls will you need?
Okay.
100 calls. Factorial 1000 calls. So in this global memory, depending upon what is your input to factorial, the amount of global memory needed will change, and that is never a good thing to have, because global memory is fixed for the program. Have we talked about the base and bound registers?
Base and bound.
Base and bound
No.
in the beginning of the class we did now. So each program has a base register and a bound register. Base register means is the first line of address. Right? Is the first line of is the address of the first line of code that is stored in the base register. We will use them in this class. So the base register is it stores the address of the first line of code of any program. And the bound register says that base plus bound, that is the address up to which you can write, up to which you can use. So for every program there is a base register and a bound register. If a program tries to access any memory outside base and base plus bound, then it's stopped. You cannot access any more memory. So now, since this memory, this global, so this is all part of the global memory. So within base and base plus bound, you should have the global data, you should have program, you should have stack as well as heap. All 4 things should be within base and bound. Now if you have global data, how is global data allocated? At the beginning, even if when you are compiling, you exactly know how much global data you need, right? So you allocate a fixed amount of global data. You know exactly how much code memory you need. So you allocate a fixed amount of code memory. There is no provisioning for incrementing the global data. There is no provisioning for incrementing the code size. But when a operating system gives memory to a program, it gives an arbitrary stack plus heap memory, because stack and heap are dynamic. It doesn't know how much memory is needed for stack and heap. So as the program goes on, it can request for more stack, more heap, but it cannot request for more global. It cannot request for more program data. It can request for more stack, more heap. Yes. So now if it cannot request for more global data and you have this kind of a program and you are saying that all local variables are kept in global data memory, then what will happen is depending upon the input n, you would need more or less global data. You will have to increase the global data memory. And there is no provisioning to do that. You cannot increase global data memory. Global data memory cannot be variable. So you cannot put local variables in the global space. There has to be separate space. That's why you put local variables in stack, because stack is dynamic, can change size. Do you understand why you cannot have n in the global data memory? All local variables and functions have to be in the stack. So that's why you have stack memory for each function. Stack, or it's also, it used to be called scratch memory before, like long time back. Stack memory was also called scratch memory. So we will talk about the stack. Stack is essentially the scratch memory for functions. It is used in all the different kinds of processors the general purpose processors. Now, as you know, stack is last in, first out, right? Whichever enters last gets out first. So in order to emulate that, what people have decided is that stack should start with high memory addresses and it grows downwards. Right? So it starts at high memory address, which means bigger addresses, and whenever you put a variable in it, the stack pointer will be decremented. So it goes down from high memory addresses. So if you think about it, if there is a program and you have base and base plus bound, you should keep the stack at base plus bound. Right? Whenever you push a number into the or an item into the stack, you do base plus bound plus 1. So which means the address decrements. So base plus bound minus 1. Right? So all these down addresses are more, the up addresses are less. So it starts from 0 and then you increment the address. Right? So that's why a stack starting from high memory addresses means it is starting from down. Right? And it grows down means that the addresses go down. Like from higher values it goes lower values. But if you are thinking of up and down, then that means the stack pointer goes up. So this might be confusing. This might get confusing. So let me reiterate. So the stack address should start from higher memory addresses. So from higher memory addresses, the convention that will follow is memory address starts from 0. So the top means 0, the up means 0, and then it starts increasing the memory address. As we go down, it increases. So the stack pointer starting at higher memory address means stack pointer starting at base plus bound, which is just at the bottom of the code. If you enter a variable into the stack pointer should go up, which means the address should go down. Right? So it's very confusing to understand, but we will try to understand as and when we see some examples. So functions are free to push registers or values onto the stack, pop values from the stack into registers. They can do all those things. The assembly language supports this on x86. So what are the registers? ESP. The ESP register holds the address to the top of the stack. So there is a specific register in the CPU that is reserved for keeping the top address of the top of the stack. The ESP register. ESP register has the top of the stack. Now push EAX or push EDX, whatever you want to do. But let's say we do push EAX. If we do push EAX, then what happens? It decrements the stack pointer, which means from higher address it goes to lower address. Right? Decrementing stack pointer when it moves up. Right? So when you do push EAX, it decrements the stack pointer, then stores the value of EAX to the location pointed by the stack pointer. So if you decrement stack pointer, then ESP has that decremented value. Right? So whatever location ESP stores, in that location you have to put the value of EAX there. We'll see an example that will make it clear. Right? So push means you decrement stack pointer, and whatever location is the ESP is holding, in that location put the value of EAX. Then pop. Pop EAX does what? Pop EAX stores the value at the location pointed to by the stack pointer into EAX. So whatever the location was there in the stack pointer, whatever value was there in that location, you take the value and store it into EAX. And then what you do? You increment the stack pointer, which means you move the stack pointer down. Right? So these are two operations, push and pop. Now let's see an example. So now this example confuses you more because now we are reversing. We are saying that no, the start address is not 0. Let's say the start address is 0 at the bottom. So now it's reversed. So which means the stack should be at the top. Whenever we push, the stack should go down. Whenever we pop, the stack should go up. Right? Because now the lower addresses are below and the higher addresses are up. Right? So let's say we have the stack let's say this is the scenario, right? This is the scenario. We had the stack, something happened, and we had the stack here, 0x100000. Let's say that is the situation, the current situation. The stack is there, everything else is garbage below, right? And the stack pointer is right there. Let's say the value at EAX is A, and the value of EBX, which is another pointer, and another register, the value of EBX is 0. The stack pointer is this one. Now what happens when we do push EAX? So let's say we are doing push EAX. If you do push EAX, then what should happen? So push EAX means whatever value was in EAX, right? That should go into the stack pointer location. No, what was push? I'm getting confused. So push was, oh no, push first decremented stack pointer. So push has to first decrement stack pointer, then it stores the value of EAX into the location pointed to by the stack pointer. Right? So push has to decrement. So now if you decrement stack pointer, so if you decrement 1 0 0 0 0, what happens? If you decrement it by one memory address, so what value should it have? So remember, this is a 32-bit system. So if you decrement once, by how much should you decrement? You should decrement it by 4, because it's a 32-bit system. So if you decrement 1 0 0 0 0 by 4, what will you get? No, that's decimal. You should get FFFC, right, in hex. So you should decrement stack pointer in hex, not in decimal. Right. So you should get FFFC, So now you decrement stack pointer became FFFC, right? So if you decrement stack pointer means it goes down because lower addresses are below, right? So it went down from 1000 it went down. Now what do? You take the value of A and you put it in that location, right? You take the value of A, put it into that location. That is what happens when you push. Now you do pop EVX. What does pop do? Pop first takes the value, whatever value is in the top of the stack, takes the value, puts it into the EVX register, and then increments. Right? So what you will have is that the top of the stack has A, so now EVX becomes A, right? And then you increment the stack, so stack becomes again 10000. So you go up. So that is how you are operating stack. So now we have to grasp this concept because there are a lot of confusing things. So now what we will do is our higher memory addresses are at the top and the lower memory addresses are at the bottom. So we start from 0 at the bottom and then go up, right, at higher memory addresses. Now whenever we have a stack, let's say so each memory address will have a location, will have some location. Now if we are pointing at this line, then that means we are pointing at the value inside this box. So the line, just the box above that line, right? We can update the value inside that box just above that line. That is our convention. That is how we are drawing things, right? So top of the stack, before doing any push or pop, top of the stack has this value. This value you don't know what it is. It's just garbage, something. Top of the stack has that value. Now when you pushed, what did you do? Push first decrements. Always remember this. Whenever you push something into the stack, it will first decrement. It will first decrement. So which means the pointer from here goes to here, and it becomes FFFC. And then whatever you pushed, so you pushed EAX has the value A. It goes into this memory location. So a stack pointer was pointing here, and hence it went into this memory location. That is push. When you pop, remember you take the value first. You don't increment or decrement. You take the value first. So whatever was in the top of the stack was this, which is actually the bottom of the stack. If you think like that, like up and down, if you think. So the top of the stack was this A. You take that value, put it into the EVX, and then you increment. Right? So you increment it and go back here. So you have to understand this very well before we can go forward. How we are doing push and pop of stack. So any doubts? Do you have any doubts? Anybody has any doubts regarding this stack operation, this basic stack operation?
Is this tied to a certain CPM or similar instructions?
No, this is
In general.
how it happens in all CPUs. This is a general runtime environment.
If you have a longer float type, it should decrement by a larger number. Like if it takes.
Yes, if you have like 8-bit numbers, you should decrement by 8 bits. Because you need to keep, split up that float and use 2 memory locations.
So how does the machine know how much to decrement? Because just based by push.
Based on the instruction. Either you are doing move or move L, and if you are doing move, then you have that. So when we did the float example, When it is this float example, we move that big number. So that big number cannot be represented in single register or in single memory location. You have to have two memory locations. So by just executing that line of code, the CPU will know. So everybody understands this stack example. How to push and pop. Okay. Now we go into another concept. Function frames. You might have not, you might already know about this. Function frames means each function has a separate stack, has its own stack. So functions would like to use the stack to allocate space for their local variables. The question is, can we use the stack pointer for this? Turns out yes, but we have to be very careful, right? So the stack pointer can change throughout the program execution, and we need to take very good care about stack pointers. So now if there is now there can be multiple functions, right? There can be multiple functions, but there is only a single stack pointer. So how do we use this single stack pointer to maintain multiple function frames? So that's why in addition to a stack pointer, you have a frame pointer. So what does frame pointer do? Frame pointer points to the start of the function's frame on the stack. So what happens is that for each function you have a frame pointer. Frame pointer points to the start of the stack for a particular function, and then stack pointer changes. Stack pointer can change, and you know whether this is in a particular function frame or not, because by using the frame pointer. Right? So there are two pointers for each function. One is the frame pointer, which points to the start of the frame of a function, and the other is the general stack pointer, which keeps on changing. Right? Frame pointer does not change. It always points to the start of the function's frame. So once a function is called, frame pointer does not change. But for two subsequent calls of functions of the same function, you called it twice, let's say. The same function you called it twice. It can have different frame pointers, depending upon what you did in the middle. Right? So two different functions can have two different function calls of the same function can have different frame pointers. But once a function is called and it's executing inside that function, frame pointers don't change. Only the stack pointer changes. Yes.
So then for recursive calls, it's going to stay on the same frame pointer.
No, recursive calls two different functions. So when you do recursive calls, you get different frame pointers. You start getting different frame pointers. That's why you should avoid doing recursive calls, because recursive calls put a lot of load on the memory. Each time you are calling the same function, you are getting a different frame pointer. You are maintaining a different stack, a different function frame. So it is increasing the stack size. So that is the reason that you should avoid recursive functions. Recursive functions are no good. You should try to do it using for loops. Yes.
The frame pointer is a stack pointer, obviously. Frame is a
No, frame pointer is not exactly the stack pointer. The moment you call a function, frame pointer is the same as stack pointer. But when you are executing inside a function, stack pointer can change.
Okay.
But the frame pointer remains the same at the start of that function frame. The stack pointer changes. Does that answer?
So it's another type of stack pointer.
That's what I'm saying. It's not the stack pointer.
No, but it's another type of stack pointer. It's not a different structure.
Oh no, it's not a different structure. It's still a pointer.
So
Yes, it's still a pointer, but you cannot call it stack pointer, because stack pointer is dynamic. It is changing. Frame pointers for a particular function call does not change, but for two different function calls it might change. But once you have called a particular function and you are executing inside it, frame pointer don't change. Only stack pointer changes. Does that answer? So each local variable will have different offsets of the same point, of the frame pointer. So from a frame pointer, you can say that you can locate a particular variable by adding an offset to the frame pointer. So if you have a new variable, then you can have that fixed frame pointer and add an offset to that frame pointer, and you get the location of that local variable. So that offset can change. That offset is different for different local variables, right? So frame pointer remains fixed, but the offset with respect to the frame pointer, that changes. So in the x86 architecture, frame pointer is called the base pointer of a function, and is stored in EBP. So EBP is a register to store a base pointer of a function frame. So that frame pointer is also called the base pointer, and it is stored in EBP register. So we'll see an example. Let's see an example. So it's the same example that we had. Instead of having ABC as global, we have ABC as local. So what happens? Let's see. So now this is a function. Int main is a function. So since it is a function, it will have a frame pointer, right? So that frame pointer will be where? It will be in EBP register. Do you understand this? Main is also a function, so it has a frame pointer, EBP, right? This base pointer is same as the first line of or address of the first line of code, the base register that we call it, EBP. EBP is the base register, so it also has the address of the first line of code. You also have a bound register. We are not dealing with the bound register here. So the base register is in EBP, or the value of the first line of address. The address of the first line of code, that is stored in EBP. So for main also, you will have an EBP. That EBP is the first line of code. Now where do you store A? Remember we said that you have a frame pointer and then you have an offset. Let's say the offset for A is capital. So you store A, small a, the local variable, at that base pointer EBP plus A. That base pointer is also the frame pointer. And where do you store B? B will also have an offset capital B. So you store the base pointer plus capital B. That's where you store B. C, similarly, you store that base pointer plus an offset. Now what you do when you put A equals 10? Where does 10 go? Yes? Where does 10 go? Does it go into the global memory? Global data memory, does it go there? Doesn't go there. Where does it go there? It goes into the stack. So which location in the stack? EBP plus A. So remember, EBP was our frame pointer. So now this is stack. EBP is starting from EBP, whatever we have is stack for main. As the main function stack. So EBP plus A, you put 10 in EBP plus A. So 10 goes into the stack memory. Similarly, EBP plus B becomes 100. And so does EBP plus C, becomes 10.45. Then what you intend to do is you intend to put the, you add A and B and put it into the stack where A was there. Right? Stack allocated to the local variable A. So that is the intended operation. Now let's see what is the operation. So what really happens is this. So A goes to EBP minus C. Why minus? Yeah, one at a time. You want? Yes.
When push it decrease first.
Yes. So what do you mean by storing A in EBP plus A? That means you're pushing it into the stack. So if you push, you decrement first, and then you put the value in. So if you decrement first, then EBP has to be decremented, EBP minus C. Now remember, EBP is not decremented. EBP remains the same, so frame pointer remains the same. Frame pointer doesn't change. But what changes is the offset. The offset is minus C. That is changed. So now EBP minus C, and that is the top of the stack. So stack pointer has changed. Stack pointer now becomes EBP minus C. Frame pointer remains the same, EBP. Frame pointer is in EBP, stack pointer becomes EBP minus C. And you put the value of value 10 in there. Right? We haven't put the value 10 yet. We have reserved the location for it. The location for B becomes EBP minus 8. Now why minus 8? Why did it become minus 8? C minus 4. Right? That's good. C minus 4. And then you put the value of C in EBP minus 4. Basically 8 minus 4. Right? Then what you did, what you need to do in order to put value 10 into EBP plus A. Now remember, what did we do before? We did move L. Why? Why did we move L? Because we had a global data memory in there. Now we don't do move L. What we do is this. So what is this? We are taking the ESP, or no, we are taking the EBP, putting it into ESP.
Oh no, there is some problem.
Just one. Okay, this will make more sense. This will make more sense. So what we do here? So now remember, we want to put the value 10 into the location of A. We want to do that. So what we do is we first take the base pointer, which is the frame pointer, put it into the stack pointer. Right? So we took the base pointer, put it into the stack pointer. Then we subtracted the value 16. So 10 is in hex. So we have to subtract the value 16 from the stack pointer. So if we do that, then where do we go? So we subtracted how many times? No, we subtracted 16. So we subtracted 3 times. No. If it's 16, we subtracted 4 times. Okay, yes, we subtracted 4 times. So we subtracted 4 times, and then we move the value A to EBP minus C. So that is the assembly code for just putting the value 10 into the memory location A. So let's revisit. So what we did, we moved the the move instructions for the mass problems. Okay, so move stack pointer. Okay, now okay. So first you move the stack pointer into the base pointer. So what was the stack pointer initially? We didn't really change the stack pointer. But when we didn't push yet. We associated the locations of A, B, C with those EBP minus C, EBP minus 8 and EBP minus 4. So the moment we do that, after we stored C, then we decrement again. Right? So what is the current stack pointer now? Let's go back one step. So we put A, stack pointer became EBP minus C. We put B in, stack pointer became EBP minus 8. So confusing. What does push do? Push decrements first and then puts it in, right? That is what push does. Okay, so if we want to put A in, then we decrement stack. So stack becomes EBP minus C. Put A in there. We decrement stack. Stack becomes EBP minus 8. We put B in there. We decrement stack again. Stack becomes EBP minus 4. We put in C.
Larry, what is the value, the minus the value you're decrementing? What is that based on again?
Pardon? It's based on the amount we need to store.
So then A is C because
A is C because you need 4 bits to store.
that 0xC is 4 bits.
Yes. F minus C.
Oh, okay.
Right. Do it. Let's do it.
Just where does EBP point again?
Pardon?
Where does EBP point?
EBP points to the first address. So let's draw it. If we draw it, it will be much easier. So let's say this is our 0xF, right? This is our 0xF, then this is 0xC,
Oh, okay.
0x what 8, 4. Let's say. So now let's say our base pointer was here, EBP, right? Base pointer was here. Now we want to push A. Push does what? Decrements first. So we go here. We don't put any value yet, but this is value reserved for A, right? Now we decrement again. So we go to here. That's the value reserved for B. We decrement again. We go here. That's the value reserved for C. Now what we are doing next?
But that's wait. So
Pardon?
C is a float.
Yes, C is a float.
So how would you only get?
So we can put values here. Yes.
It just seems kind of misleading because there you're subtracting C from the address of the base pointer, correct?
Yes.
So wouldn't that essentially make A go into address 4 as F minus C? Because the way you're stating it
Oh,
here says that you're putting it into address C.
Oh, yeah.
So that's like what's confusing me. So it should be CB.
Okay, so let's do that.
Minus 0x4.
Yes, let's do that. And so on. Actually, let's not have numbers. If we have numbers, there will be problems. So let's draw it again. So let's say we have EBP here. So now what we are doing is EBP minus C, which means how many? 3 times. So this is minus 4, this is minus 8, this is minus C. So this location is put for A. This location is put for A. Then we do EBP minus 8. So EBP remains the same. We do EBP minus 8. So once and twice, right? So we keep this space for B. Then we do EBP minus 4, which means just once.
Okay.
C. Right? Then let's say what is the next step? We move ESP to EBP. Now initially what was ESP? So if we move ESP to EBP, then what was our top of stack? The top of stack we first pushed A, then B, then C. So EBP remains, ESP is the same thing. It becomes the same thing. EBP is ESP. Right. Then what we did subtract 16 from ESP. Right. So 16 from ESP means what? You 4 times. 1, 2, 3, 4. This becomes ESP. Then you move A into EBP minus C. So what is EBP? This one. C minus C is how much? 1, 2, 3. So this was reserved for A. You did 0xa here. Right? So that is what we wanted to do. Anyways. Then what is the next thing that you do? Not you as in the compiler. So you move 064 into EBP minus 8. So this is EBP minus 8 means 2 times. You have 0x64 here. Then what you do? You put 0, 4, 1, 2 that big number into EAX. So somewhere EAX has that number. 0x41273333. Then you put EAX into EBP minus 4. So EBP minus 4 is this, right? So you put this value. Now this value you cannot hold it just here, right? But you have 2 spaces. So you put this, take these 2 spaces, put that value here. Then we move, okay, yeah, we do that. Then move, okay, now we are trying to execute the function A equals A plus B. So what do? You move EBP minus 8 to EAX. So EBP minus 8 is what? This one. EBP was this one. So 1, 2. So EBP minus 8 means 64. So EAX has now 64, right? Then you do add EAX and EBP minus C. What was EBP minus C? 1, 2, 3. So EBP minus C is A. So what you are doing is you are adding EAX. So 0x64, you add it with 0xa, right? And you are storing it. Oh, there is some more step. I skipped those. So you are basically storing it in 0xa again. So in this place, you are storing it again. So now the stack pointer is here, the EBP is here, and that is what the system does. So this is how the stack is being manipulated by this code. Now we have to make sense out of it. Right? We have to make sense out of this. Now how to make sense out of this is what runtime execution does. So we have to discuss an algorithm that the runtime execution engine uses to manipulate the stack and base pointer in this way. We'll talk about that algorithm. Maybe we should start next class. We'll talk about that algorithm next class. Right. So next, what we'll do is we'll see how this function frame is manipulated by this code. Right. Actually, let's just do it. Briefly, let's just go through this. Because it's similar to what we did. So what happened was, let's say this is our stack. Initially, the big address is at the top and the small address is at the bottom. So let's say that is our stack pointer. Initially, that was our stack pointer. So we move, and we keep track of EAX, ESP, and EBP, right? So the first instruction is move ESP to EBP. So EBP becomes this, right? Then the next instruction is you subtract 10 from ESP. So ESP becomes 0FFO. So that is where? That is somewhere here, right? So 4 times you decrement the 4 elements. Then you move. So these are the different addresses. So 0FFC is 1 decrement, then 0FF8, 0FF4, and 0FF0. Now, anybody knows why we decrement, why the system decrements it 16 times, by 16 value? Why does the system decrement the stack pointer by 16?
Those are local variables.
So now, yes, this is the decision taken by the runtime environment. Now, whether it is 16 or whether it is 20, 40, depends upon the runtime execution engine. But why it is decrementing initially? It is decrementing to make space for all the local variables. So whatever local variables it can account for right now, it decrements. It keeps space for that. Now it is the runtime execution engine doesn't know in the future how much local variable you will need. It does not know. So initially it does a rough estimate of how much memory you need. Now in this case, it does the estimate that A, B both need 4 bytes and C need 8 bytes. So 4 plus 4, 8 plus 8, 16. So I will decrement by 16. But another runtime execution engine might make a different estimate. It might make more. But one thing is common is that before starting execution, before going forward, before storing variables, before adding variables, one thing is same for all runtime execution engine is that they will make space for local variables. How much space depends upon the runtime execution engine. Here it is 16 because we have to take 2 integer variables and 1 float, but it can be different for different runtime execution engine. So that is why we first decrement the stack to keep space for all local variables. Then what we do is, based on the EBP, right? Based on the EBP, we start storing A's, B's, and C's, right? So what we do? First, we store A. Now, why did we do EBP minus C? Why did we do EBP minus C? Why not EBP minus A? No, EBP minus 4. Sorry. Why don't we do EBP minus 4?
Taking into account the other variables.
So the thing is, we are declaring int A, B, C in order. So C should be at the top of the stack, right? So that's why we do that. Right? So it does EBP minus C and then puts A. Then we do EBP minus A 8 and put 64 in there. Then we want to put this big number So we put that EAX, that big number into EAX, and then move EAX into EBP minus 4. So we put it there. Now again, it cannot hold that big of a number. But if it's a 32-bit line, and this float is not a 64-bit, if we use a 32-bit number to represent a float, then it can hold. Then this line can hold that big of a number. If it's 32-bit, it can hold. Right? In some cases, it might not be able to hold. So that is a different runtime execution engine. But for this one, it can hold because how many numbers are there? How many bytes are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes. So 8 bytes, this line can hold because it's 32-bit. So then what we do is we move EBP minus 8 to EAX. So EBP minus 8 became what? 64. So 64 goes to EAX. Then we add EAX to EBP minus C. EBP minus C is 10. So 64 plus 10 becomes 06E, and that is the value we have in A. Okay. So this is exactly what we showed in that note. Right. So that's how this particular code operates the stack. Now, what is the general rule? We'll see maybe from next class. So we'll stop here today, unless you have some questions.
Just like an isolated.
Okay, I'll see you.
Because we have the scope of your parsing this code, then you have statement list. Right? Now statement list can be a statement which is a scope. Statement list can also be a statement list. So here what you can do is you can parse statement as statement list, and this statement list becomes a statement. So it's two statements one by one, and each statement can be scoped. So how do you parse this? This you can parse like this. So first you use the rule program. You can first use the rule program goes to global values is epsilon, and scope, right? So you parse this scope goes to S3. Okay?
Yes.
So now this scope you can you will pronounce it as IE, Ilgrade, then you public words, private words, then you get statement list. Statement list, and then you for the address. So first one is done. Now statement list can go to statement list. Right? This statement list, you can further go to statement list goes to statement. Now this statement, each of these statements can go to statement. So what you can have is you can have S3 scope, and then you have S1 and S2 scope. But you will not have a program that has this. That simply has this. Just two separate. So you won't have that kind of program. The program will have one overall scope. Because inside one scope you can have two separate.
Going back to what we were doing today, so this program is you labeled this A, C, and one. This is all that we got.
There's no difference. You can name it the other way.
Well, looking at all that.
Oh,
Yeah.
So this is not the same as.
Actually, if you need to rewind back, if you
This is not
get
same
your
as that. Okay. So I should have said X, Y, and Z.
Okay.
So this is not the same A as A that we have.
Right. I was just looking at this. That's what we do. I mean, you do have here, into here, B, here, here, and that's what he has. More elaborate. So those values should work into
Yes, yes, you're right.
But then this one was just a random.
Just a constant. No, because we want to add here.
Oh, so the
So
one
what ADA does is that it multiplies these two, EDX and this one, multiplies these two and adds VDX.
oh, okay.
So that is the function of ADA. So using ADA, we want to add A. So that's why we have this as one. Because you multiply one with A, so it remains A.
We would want to add like we did.
Yeah, we could have used that also.
Yeah,
We could have used
So
that.
it's just two.
Yes.
Okay. That makes more sense.
Yes.
Public variable.
What is the real stack with linked list or stack of
No, you implement stack with linked list.
So it's been a stack as so
Yes.
like something I think it's like I was like I did like we gave us like SD1 people as well. So we want to initialize that. We use you or use that.
Use now.
Use malloc. Doesn't
That,
matter.
that will be easier.
Easier. Okay.